Hello, I welcome you all to this another interesting screencast. The problem reads, the 0.2 kg pin P is constrained to move in the smooth curved slot, which is defined by the lemniscate R equal to 0.6 cos 2 theta in meters. Its motion is controlled by the rotation of the slotted arm OA, which has a constant clockwise angular velocity of theta dot equal to minus 3 rads per second. Determine the force arm OA exerts on the pin P when theta is equal to 0 degrees. Motion is in the vertical plane. This problem is coming from the Engineering Mechanics and Dynamics 14th edition by R.C. Hibbeler. Let's add some details. So we do have this coordinate that we are calling the radial coordinate. Maybe let it go up to there, like so. So one defining the path, and since this movement or the rotation is clockwise, I will have theta in that direction, like so, perpendicular to the radial. Okay, then this the slotted arm will exert a force on the pin perpendicular, like so. Okay, so this is the force exerted on the pin, right? So we have that force, and then we have something else. At this point, at the tangent point here, okay, maybe somewhere there, like so. Is it? Maybe at that tangent point, we expect a reaction normal force, okay, in that direction, like so, on the pin, right, like so. That's a normal force, and then we do have the weight of this let's say the weight is going to be coming up like so. All right, you have the weight. What else? I think this is basically about it. So we have the force F, we have the weight W, and we have the normal force N. But each one of these will have the components along R. We need to write them, and theta. But we need the angle. So this angle here, let's extend this line. From this point. No, I use the same black, so that is continuity. Okay, let's extend this line like so. So what do we have? And then we extend this line also down there. From this point, I extend it up to there. All right, great. So we do have this angle here. We need to make mention this one here. This one here is psi. This one here is psi. Okay, so this is psi, and then we do have this angle here. we have this angle, we do have this one there. So we know that if we are to do this, right, let me draw something. We know that if we are to extend a line like so there, horizontal line, we know that this angle here will be equal to theta, and if this is theta, then it means this one here will be 90 minus theta, and therefore this one will be theta. Okay, so we know what theta is, so let me just remove this now. So this one here is theta. We agree? I've shown how that has resulted to become theta, because we need that information. And then here we do have this one here. So we have psi like so. So if we have psi like so, and then what else do we have? Therefore, if this is psi, it is the same as this one here. Okay, therefore this one here we'll call it this one here we are going to call it alpha. Okay, we'll call this alpha, right? And our alpha is nothing but equal to our alpha. Okay, our alpha will be nothing but equal to 90 minus psi, right? Yes, great. So this one is all right. There we go. This is negative. All right, this is a negative one, right? This is negative, and so is this one here. All right, so this one here is a 90 minus psi, and we need it. So let's write down the components of these particular forces. So we'll have a component in this direction. We'll have a component in this direction for the normal force, as well as in this direction, as well as in this direction. We'll have a component for the normal force, and then for the weight, we're going to have a component in this direction. We'll have a component in this direction for the weight, as well as there we go, this direction, as well as in this direction. Okay, what else? That is about it. And then we'll have another component for the force F in this direction, as well as in this direction. Okay, as well as where is the force? This is theta, and the force seems to be in the same direction with our theta. All right, so for the force it is just all fine. For the force it is fine. All right, so we do have this component, and this component is for the weight. All right, let's label them. So this one is for the weight. Let's begin to label them. This one, this is W, This is W sine theta, and then this one is W cos theta. Okay, and then we do have this one here. This is in black. Okay, so this one is n sine alpha, and then we do have, there we go, and then this one is n cos alpha. Okay, so we have n, we have w, we have f. So this is really about it. We can show also the kinetic diagrams in this direction like so, as well as in this direction. Okay, so this is our M. So MAR, this is our M theta like so. So let's go ahead and apply the equations of equilibrium, but before we do so, let's compute all the components that we need for our acceleration in the r and theta direction. Alright, let's begin. Let's start with our r. So r is just equal to 0.6 cos 2 theta. So r dot just becomes equal to 0.6 by 2 theta. So by 2, that's 1.2. This becomes 1.2 theta dot. Then that becomes a minus there. So cos, when it changes to sine, when we are taking derivative, it becomes minus. So minus 1.2. I'm evaluating them in advance. 1.2 theta dot sine 2 theta. In r double dot, we are going to use product rule. I'll factor out this. So I'll find the derivative of one function, then the other one remains constant. So theta double dot just sine 2 theta, and then plus 2 theta dot squared cos 2 theta. Okay, get it? Of course, you do get it. Why not? And then theta is just equal to 0 degrees, and theta dot is given as equal to minus 3 rads per second, and theta double dot is just equal to this is constant, and because this is constant, we expect this to be equal to 0. Okay, let's find the values. So r at theta equal to 0 degrees, this is just going to be equal to 0.6 cos 0. So this is just 0.6, right? And then we have r dot at theta equal to r dot at theta equal to 0 degrees. This is just equal to minus 1.2 times theta dot, which is also a minus 3. Then sine, of course, 0, 2. So all this is just 0. So r double dot at theta equal to 0, this is just going to be equal to, so this one is 0, the other one just becomes minus, that is 2 times theta dot squared, which is 3 squared, becomes a positive, okay, 10 times 1.2. So this becomes a 21.6. So 2 by 3 squared cos 0 times 1.2 minus 21.6. Alright, I guess this is all. Let's now work out the values. So AR is just equal to R double dot minus R theta dot squared. Therefore, our AR is just equal to minus 21.6 minus R, which is 0.6 times 3 squared. Okay, and this we get just a minus 27, like so. So let me repeat this. So minus 21.6 minus R 0.6 times point dot squared. This is just minus 27. Then we have A theta, which is just going to be equal to R double dot plus 2R dot theta dot. Our A theta therefore is just equal to, this part is 0. This whole part goes to 0. Then we just remain with the other part, which is 2 times. Also this part is 0, right? This part also, R dot, this part also is 0. Come, because of R dot, right? R dot is 0 and theta dot is 0. So this is 0. So this makes the problem impact much simpler. Then we have tan phi, we need phi is equal to R divided by dr d theta. Our dr d theta is equal to, we know that our R is just equal to 0.6 cos 2 theta. Therefore this just becomes a 1 point, factor minus 1.2, the 2 comes this side, and minus 1.2 sine 2 theta. Alright, let's work out this now again. Let's work out this. Alright, so we have tan phi is just equal to 0.6 cos 2 phi divided by 1.2, that's minus 1.2 sine 2 phi, and this is just equal to minus infinity. And making psi subject to the formula, this just gives us a minus 90 degrees. So this just simply means it's in the clockwise direction. So we have found psi, and our alpha therefore, which is equal to 90 minus psi, is just equal to 0. Again, don't consider this negative, just simply means it's in the clockwise direction. Okay, this just means clockwise. All right. Okay, so this will just be equal to 0 alpha. Right, so with this we can now apply the equations of equilibrium. We'll say summation of forces in the other direction equal to ma r, and our r is in this direction like so. What do we have? We do have, let's check in that direction, r. We have n cos alpha. What else? Then we do have minus w sine theta. What else? That's about it. And this is just equal to ma r. Therefore, this cos 0 minus w, which is just mg, and we know what these values are. This is just a 0.2 by 9.81 sine theta, which is just 0 degrees. Then this is just equal to 0.2 times AR, and our AR is just a minus 27. Right, then our value of n will just be equal to, this part goes to 0. Therefore, our n is just equal to 0.2 by 2.7. 0.2 by 2.7. Right, sorry, 0.2 by 27. Right, 27 is AR, so that is 5.4. So it's minus 5.4. This minus just means our assumed direction was supposed to be in the other direction. Okay, so let's apply now again the summation of forces in the theta direction. This is equal to m theta, like so. So this is going down. Okay, what do we have? We have w cos theta plus f minus n sine alpha, and this is equal to ma theta. So this is just our mg, and our mg is just 0.2 times 9.81 cos theta, and our theta is 0 degrees, so plus f minus n, which we calculated as minus 5.4 sine 0, and this is equal to 0.2 by a theta, which is 0. Therefore, our f just becomes equal to, our f is just equal to, our f is equal to our f is equal to minus, so minus 0.2 by 9.81, okay, 1.962 newtons. Therefore, F is equal to 1.96 newtons, and instead of going down, this is going to be going up. I'll show this, and our n is equal to 5.4 newtons. So let me show the directions at theta equal to 0. So F will be going up, okay, and N will be going down. Alright, I think this is about it. And I hope this particular video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and I'll see you in my next screencast.